to my today's session on EMF, electromagnetic field, Maxwell's equation. Myself, Dr. Sayanti Chatterjee, Associate Professor of Electrical and Electronics Engineering Department, IARE. Today we will start the Maxwell's equation. This is the base. We can tell Maxwell's equation is the base of the electrical engineering. Maxwell's and Faraday both have created the pillar on which the today's modern age is standing. We cannot use any electrical apparatus or any electrical engineering without these two persons. That's why Maxwell and Faraday's are known as the fathers of electrical engineering. So Maxwell gave four equations. Maxwell's equations, there are four equations together and all equation has one integral form as well as one differential form. Together form a complete description of the production and interrelation of electric field and magnetic field. All the wave, say one light wave, sound wave, mobile wave, whatever the wave we know, all the wave is the electromagnetic wave. So Maxwell first gave the idea about the electromagnetic wave. The full name of Maxwell is James Clerk Maxwell. So his full name is James Clerk Maxwell. In the 19th century, he first given his law on the Maxwell's equation. Before almost 60 to 100 years back, Faraday first given the Faraday's law. But Faraday's law is totally experimental. Maxwell's proved it experimentally as well as mathematically. So this experimental laws was first given by Maxwell, and that's why these four equations are known as the Maxwell's equation. The statement of the four equations are respectively: electric field diverge from electric charge, an expression of Coulomb's law, and first one. So what is the first one tells? First one tells electric field. What is the meaning of the electric field? If we keep one charge, it will create some field, and this field is known as the electric field. So electric field diverges from electric charge and it gives a new expression of the Coulomb's force. So if there is a charge, positive charge, it will give some flux in the outward direction. If there is a negative charge, it will come in the inside direction, and on which this electric will diverge or converge from the electric charge, and this is a modified Coulomb's law. What is the Coulomb's law? If there are two charges, there is a force of attraction and repulsion, and the force is directly proportional to Q1 Q2 by R square. So we can get the idea, the modified vector form of this force using the first law. Then as there is, in the case of the magnetic field, so as I told, one is for the electric field, same law he given for the magnetic field. When we are thinking about the magnetic poles, like electric poles, there is no isolated magnetic poles. Magnet, if we find one magnet, it always have the two poles, north pole and south pole. Only north pole or only south pole cannot practically feasible. So there is no magnetic poles. So for the Coulomb's force on the magnet is first given in his second law. Then he gives the electric fields are produced by the changing magnetic field, on which the transformer and generator, all the equations already manifested. What is this? If there is a time varying magnetic field, there is a rate of change of flux, and due to the rate of change of flux, there is an EMF equation. So this modified Faraday's law is discussed in his third law. And if the similarly, if the magnetic field is circulating, it will produce some charging electric current. So are the motors experience. These are based on the motors. So Maxwell's, this is the extension of the Ampere circuital law to include the interaction of the charging field. So we got the four equations of Maxwell, namely modified Coulomb's law for electrostatic field. Secondly, the modified Coulomb's law for the magnetic field. The first law is also known as the modified Gauss law. Third one is the modified Faraday's law on the electromagnetic induction. And fourth law is the modified Ampere circuital law. So these four equations are discussed here. So Maxwell's four equations that together form a complete description of production of electric and magnetic charge fields, as we discussed. So as I told before also, just same thing. Gauss laws for static electric field. First law is the modified Gauss law for the electrostatic field or static electric field. Second law is all about the Gauss law for static magnetic field. Third one is the Faraday's law about the time varying or changing magnetic field, which produces the electric field. This is the working principle of generator and the transformer. And Ampere-Maxwell's law or Ampere circuital law tells the changing electric field. This is the changing magnetic field. Magnetic field is time varying. Here electric field is time varying, which produces the magnetic field. So for the power system applications, we are getting this in our power system applications. So Maxwell's equation has the four equations together. First equation is the Gauss law for electrostatic field. Second law is the Gauss law for electromagnetic field. Third is the Faraday's law, which says about the changing magnetic field. And fourth law is the Maxwell's law, which says a changing electric field, which produces a magnetic field. So the combination of equation 3 and 4 explain the electromagnetic wave. The combination of 3 and 4 gives the combination of electromagnetic waves such as light, which can propagate by its own. We know that for light wave, X-ray wave, sound wave, this electromagnetic wave doesn't need any type of medium, so it can propagate on its own. The combination says that the changing magnetic field, this combination change from the third we can tell the changing magnetic field produces a changing electric field. If there is a changing magnetic field, there is a changing electric field. Similarly, this is the one important point of this. Changing magnetic field produces a changing electric field. We take one example of a generator. Or we can take the example of the transformer. In the case of a transformer, when we are giving the current, when current flows through the primary, it creates some flux. And the flux due to the AC, the flux is the time varying magnetic flux. And when there is a time varying magnetic flux, there is a rate of change of flux which induces the primary EMF. So primary EMF induce the secondary EMF in the transformer. We know this, that with a simple example I will show you that if this is a transformer primary and this is the secondary, when we are giving the primary current I0, it will flow through the coils and it will create some flux. The flux phi is due to the AC. So what will happen? The flux is also time varying. As the flux is time varying, it will induce some EMF. So this EMF is also the AC or time varying in nature. E1, primary EMF. Primary EMF will induce the secondary EMF due to the electromagnetic induction. So we can find the changing magnetic field produces an changing electric field. So this is the first point. Now we will go to the second point. What is the second point? The second point tells about the changing electric fields produces the another changing magnetic field. So this color is very dark. So what it tells? It tells that changing electric field produces another changing magnetic field. So what is the example? When current is flowing through one overhead lines, due to that creates an electric flux, and electric flux is increase the field, which is ultimately gives the skin effect in the power system. So we can found these two things. Changing magnetic field produces the changing electric field, whereas just opposite, changing electric field produces another changing magnetic field, and thus the cycle continues and electromagnetic wave is made and propagates through the space. When these two links together, they will create an electromagnetic wave like light. So light will propagate through the space. It doesn't need any type of conductor to flow from one place to another place. So first we will discuss one important definition, flux density, and the first one is the electric flux density. Electric flux density or displacement density is defined as the electric flux per unit area, and we can write D equals to psi by S. Psi is equal to total flux and S is equal to surface area. For a sphere, the surface area is A is equal to 4 pi r square. So D is equal to Q by 4 pi r square. But we also know that the intensity of a field is equal to Q by 4 pi epsilon 0 r square. We know that the E is equal to Q by 4 pi epsilon r square. So this we get from the Coulomb's law, already discussed in my previous lectures. Please check this. So by comparing these two, we got this D is equal to epsilon naught into E. What is epsilon? Epsilon is nothing but the permittivity of the medium. And if permittivity of the medium and its value is 8.854 into 10 to the power minus 12. Now, similarly, we can write it for the electric field. What is this? This is similarly we can write B. B is the magnetic flux density. It is the magnetic flux density is equal to phi by A. Phi is the magnetic flux. A is the again cross-sectional area. So here also if we write it, we can find B is equal to mu naught into H. What is mu? Mu is the permeability. And what is H? H is the magnetic field intensity in ampere turn per meter, N into I per length. Here what is D? D is the electric flux density, epsilon 0 is the permittivity, and what is E? E is the electric flux density. So we got the two relation, and this two relation is very important. D is equal to epsilon naught E and B is equal to mu naught H. So this is the flux density in terms of the electric flux. Now we will go for the Gauss law. The Gauss law tells the electric flux passing through any closed surface is equal to the total charge enclosed by the surface. What does it mean? If we can see that the psi, what is psi? Number of electric flux is equal to d dot ds. What does it mean? Number of electric flux, I have one. Number of the electric flux. So this is a closed surface. This is full of charges. So when there is charge, there is a flux, electric lines of force. And electric lines of force or electric flux per unit area is known as the flux density. So what is told? The electric flux passing through the closed surface is equals to the total number of charge enclosed. We can write psi is equal to d dot ds, charge enclosed. So this is the Gauss law, and this Gauss law is for the electrostatic field. Gauss law is applicable for the electrostatic field. So, Maxwell's first equation is again known as the modified, as I told in the second slide, modified Gauss law. It is also known as the modified Gauss law. Maxwell's first equation known as the modified Gauss law. So, what is the Maxwell's first equation tells? Maxwell's first equation, as I discussed earlier, it can be written as the Q is equal to d dot ds. From the Gauss law, we can write Q is equal to surface integral of d dot ds. d dot ds. So, this is the Gauss law. Number of electric flux psi is equal to charge enclosed. This is the Gauss law. And what is the psi? Psi is nothing but the d into ds. Or what is d? D is the electric flux density. So we know this one, d is equal to d dot and d is equal to electric flux density. Now if we apply here the Gauss divergence law, what will happen? This surface integral will change into the volume integral. If we use this law, this vector from the vector algebra, the surface integral will be changed into the volume integral. So d will be changed into the grad dot d. D will be changed into the grad dot d. So what is grad? Grad is nothing but the del by del x plus del by del y plus del by del z. When one flux is coming out from a surface, it will go in the xyz direction. So grad is the del by del x plus del by del y plus del by del z. So when we are taking the grad, so surface will be changed into the volume. So Q is equal to d grad dot d. So again, if we write Q is equal to volume integral of rho v dv. So what is rho v dv? Rho v is equal to volume. I have discussed this before also, volume charge density. And what is rho v? Q is equal to integration of rho v into dv, volume integration. Volume charge density means charge stored per unit volume. If we have a area, we have a volume, charge stored per unit volume is known as the volume charge density. So Q is equal to rho v into dv. So if we compare this portion with this portion, we will get we will get surface integral of d dot ds is equal to rho v into dv. This equation is known as the Maxwell's first equation in integral form. This is the Maxwell's first equation in integral form. Now, if we go for the compare this portion with this portion, what we will get? We will get grad dot d dv volume integral is equal to rho v into dv. So both side is the volume integral. So we can write grad dot d is equal to rho v. This is the Maxwell's first equation in point form. So we are getting two equations, Maxwell's first equation in the point form. Another we got another one we got d dot ds surface integral is equal to integration of rho v dv. This is the surface integral form of the Maxwell's first equation. This is the integral form, this is the derivative form or point form. Point form is nothing but the derivative form only. So if we are taking some assumptions here, what are the assumptions? Electric charge Q produces an electric field E. We are thinking that electric field is constant and number of charge Q produces the electric field E. Electric field flux passing through any closed surface is proportional to the total charge content in the surface. So we are also assume the Gauss law is applicable here, and then only we can prove the Maxwell's first law or Maxwell's first equation. So this is the Maxwell's first equation. Grad dot d is equal to rho v, and we can also write d dot ds is equal to rho v dv. So these are the Maxwell's first equation in point form. This is in the integral form. This is the point form. Next we will go in the Maxwell's second equation. Maxwell's second equation is based on the magnetic field. So first one is about the electric field, second one is about the magnetic field. So from the Gauss law, we can write magnetic flux in the given flux in a surface is known as the surface integral of magnetic flux density, similar to the Maxwell's first law. But so psi magnetic flux is equals to integration of B dot ds. What is B? B is nothing but the magnetic flux density. Magnetic flux density. But as it in a magnetic field, the total flux density in a closed surface is always zero, because any isolated poles cannot stay. So magnetic flux is starting from the north pole and ending at the south pole, and the net value is zero. So total flux density in a closed surface is always zero. So we can write psi is equal to B dot ds is equal to 0. So if we again use the divergence theorem, we can write grad dot B dv is equal to 0. So we can write two equations, B dot ds is equal to 0. This is the integral form of the Maxwell's second equation, and grad dot B is equal to 0. This is the point form of the Maxwell's second equation. So Maxwell's second equation has the two part, B dot ds is equal to 0 and grad dot B equals to 0. This is the integral form and this is the point form. This is the integral form and this is the point form. So we can also assume that, so here we will show you, this is the north pole and this is the south pole as I told, and because isolated magnet is not practically possible, so flux will start from the north pole and meet at the south pole. Flux will start from the north pole and meet at the south pole, and what will happen? The total flux density will be 0. So what are the assumptions? The total magnetic flux passing through any closed surface is 0. The assumption that there are no magnetic monopoles. Magnetic monopoles are not practically possible. As I told, there are no magnetic flow sources and the magnetic flux lines always close upon themselves. Also, this is called the law of conservation of the magnetic flux. So there are 4 assumptions we are taking here. This is the Maxwell's second equation. Let's move to the Maxwell's third equation. Before Maxwell's third equation, actually Maxwell's fourth equation and third equation, someone tells third equation is the from Ampere's circuital law, someone tells Faraday's law. So we are taking the Ampere's third equation as the modified Ampere's circuital law. So what is it telling? Ampere's circuital law can be written as the line integral of magnetic field surrounding closed loop equals to the number of times of algebraic sum of currents passing through the loop. So integration of HDL is equal to I enclosed. If we check if it is a current carrying conductor, it is always cylindrical in nature. So current is flowing through it and it has the XYZ axis. So if we check from the front view, we can find that there is an imaginary circulating magnetic field is there. H dot dl is equal to I enclosed. If current flows through an coil, it will create a magnetic field enclosed to the wire. So Maxwell's third equation is based on this. From the Ampere's circuital law, we know integration of HDL is equal to I, but also we know integration of J dot ds is equal to I. What is J? J is the current density. What is the meaning of current density? Current J is equal to di by ds. So di is equal to integration of J dot ds. So current density is J dot ds. Equating the two equations, we can write integration of H dot dl is equal to J ds. H dl is equal to integration of J ds. So integration, again we are using the Stokes theorem here. If we, because this is known as the, what is this? This is known as the this is known as the Maxwell's third equation in the integral form. This is the Maxwell's third equation in the integral form. So if we write it, if we use the Stokes theorem, so integration of H dl can be written as grad cross H into ds. So if we equate this with this, we can write integration of J ds is equal to integration of grad cross H into ds. So if we equate these two equations, we will get if we equate these two equations, we will get grad cross H is equal to J. So this equation is known as the point form of Ampere's law or Maxwell's third equations in the point form. So this is the Maxwell's third equation. So what are the assumptions we are taking? We are taking here the electric current I or a changing electric flux through a surface produces a circulating magnetic field around any path that bounds the surface. We always thinking the electric field is the circulating in nature. This is one first assumptions. What is the second assumptions? Electric currents and charges and changes in electric fields are proportional to the magnetic field and circulating about the areas where they accumulate. So electric currents and change in electric fields are proportional to the magnetic field. We are taking is the exactly proportional to the magnetic fields. And we also know grad cross H is equal to J. J is the conduction current density, but there is some leakage current also, which is known as the displacement current, and it is the del T of D. So grad cross H is basically the modified Ampere's law, modified third equation. This is the modified third equation is grad cross H is equal to J plus delta D by delta T. This is the modified Ampere's law, or we can tell modified third equation of Maxwell's. And on these equations, later the generation of the electromagnetic fields depends. Now we will discuss about the Maxwell's fourth equation. You can see in the Maxwell's fourth equation, if there is a changing electric field, if this is the magnet is moving, means the magnetic field is continuously changing. So it will change means it will induce some current from the Faraday's law. E is equal to minus d phi by dt, or we can write E is equal to minus n d phi by dt. It will produce some EMF, electromotive force. E is equal to n, depends on the number of turns. So we can write from the Faraday's law, E is equal to minus d phi by dt when number of turns equals to 1. Now we will get back to the slide 1. We have already discussed total flux is equal to B dot ds. B is the flux density. It is the magnetic flux density. So we are substituting the phi with integration of B ds. D integration of B ds by dt. So electric potential, already we know voltage is equal to integration of E dl. B is equal to E dl. It depends on the E and dl. So E dl is equal to surface integral of dB ds by dt. Why? Because in the previous page we got E is equal to minus dB by dt into ds. Here we got B ds by dt. So dB ds by dt. We got it. B dP ds by dt. So we can, from the Gauss law, we can write phi is equal to surface integral of B ds. E is equal to minus d phi by dt. So is equal to minus B ds by dt. So if we equate the two equations, we will get integration of E dl is equal to, it is dl, this is surface. So we are changing into the, again we are using the Stokes theorem. So surface integral of grad cross E. So if we equate these two equations, we will get, so this is again the integral form of Maxwell's law. And here we got grad cross E is equal to minus dB by dt. This is the Maxwell's equations fourth form or vector form of the Faraday's law. So what are the assumptions we are taking? Changing magnetic flux through a surface induced an EMF in a boundary path of the surface. A changing magnetic field induces a circulating current or time varying current. the voltage accumulated around a closed circuit is proportional to the rate of change of magnetic flux enclosed in it. A circulating magnetic field is produced by an electric current and by an electric field that changes with time. So these four assumptions we have taken here, that the changing in the magnetic flux is induced the EMF, changing in the magnetic field induced a circulating current, the voltage around a closed circuit is proportional to the rate of change of magnetic flux, and circulating magnetic field produces an electric current. So these are the assumptions. Next, we just told before also what is displacement current, how it is coming, d by dt. When current is flowing through a capacitor, there is a medium. So this leakage happens through the medium. This is called the displacement current. Very small amount of current flowing through the medium or the dielectric medium. So IC is equal to C dV by dt. But we know C is equal to epsilon A by D, where A is the cross-sectional area. And D is the distance between these two. So IC is equal to epsilon by A D dV by dt. Now this is D and dV by dt. D by dt is cancel out. So we are getting epsilon into dE by dt, because V into dl is nothing but the E. So epsilon dE by dt, epsilon dE is nothing but the flux density. Already we have discussed in the slide number 3. D is equal to epsilon into E. So JC is equal to JD by JT. That's why in the modified Ampere's law, we took grad cross H is equal to actually J plus JC, and JC can be written by D by dt. So this is the displacement current. And similarly, as I told earlier, I is equal to IR by IC. IR is due to the conduction current, and this is the displacement current. Next, Maxwell's equation in the time varying field. We are considering E is equal to E naught cos omega t, which can be written as the E naught e to the power j omega t. Similarly, so D, what is the relation? D is equal to epsilon into E. So if it is a cosine function, it should be a cosine function, because epsilon is a constant term. So D by dt is equal to d omega, just differentiation we have done, and dB by dt is equal to, this is the small j, j omega b, because electric flux density is similar to the magnetic flux density. So we got grad cross E is equal to del B by del T. So we can put this and we can get grad cross E is equal to j omega b. We got the grad cross E is equal to j omega b. Similarly, then grad cross E is equal to what is b? B is equal to j omega mu h. This is all at the small j. So j omega mu h. Again, grad cross h is equal to, we got j d by dt. Grad cross h, we got j. This is capital J, because this is the current density, is equal to dd by dt. So we got is equal to sigma E plus j omega d0. So grad cross H is equal to sigma E by j omega d0, and this is known as the Maxwell's equation in the time varying field. So if we write in a one glance, first one is the Faraday's law, grad cross E, del B minus del B by del T, and E dot dl is equal to minus del B by del T into ds. So this is the Faraday's law, modified Faraday's law. Differential form, grad cross H is equal to j delta d by delta t, and here we got integration H dot dl I plus delta d plus delta t ds. This is the modified Ampere circuital law. grad dot d is equal to rho v is equal to again d dot d is equal to rho v dv. This is the Gauss law, and grad dot b equals to 0, and it is b dot ds is equal to 0 because no isolated magnetic charge is presented. So thank you, and here we have discussed the 4 topics, Maxwell's fourth equation. So thank you all.
Like, share and subscribe. Hit the bell icon for more updates.